Let's use mutual information measure to understand information redundancy. Let two neighboring image pixels have image intensity values S1 and S2. In the first image, each pixel is either black or white, takes value 0 or 1 in binary. In the second image, pixel intensities are grayscale integers between 0 and 255. On the right is a plot of joint probability distribution of S1 and S2 for grayscale pixel values. The S1 value increases along horizontally and S2 value along the vertical direction. And the brightness of each x, y location marks the joint probability for the corresponding S1 and S2 values. The brightest XY locations are along the diagonal band, in this case, where S1 and S2 values are very similar. Because two neighboring pixels are most likely to have the same or similar grayscale values, often they are both bright or both dark. Therefore, the conditional probability of S2 given S1 is very different from the marginal probability. And this is a hallmark of non-independence between two variables. And this is the mutual information between these two variables. And when this is non-zero, the summation of individual pixel entropies is larger than the joint entropy, such as the case in this example. In general, given n variables, S1, S2, S3, etc., the summation of individual entropies is always larger or equal to the joint entropy, and this summation is the coding capacity needed to represent all the signals individually in the raw input form, S1, S2, S3, etc. And the joint entropy is the amount of the actual information represented by the raw input representation. So for this representation, the redundancy is defined like this, and it always has a non-negative value. Now let's try out two examples. In the binary image, the joint probability of two pixel values can be represented by this 2x2 matrix for all the four possible combinations of S1 and S2 values. For example, the top left matrix element marks the probability S1 and S2 both equal to 0, and the bottom right element for when they are both equal to 1, and the diagonal elements are for when they take different values. We can then calculate the marginal probability of S1. So for S1 equal to 0, the probability is 0.5352, almost 50%, like 50%. And it's a summation of the top row elements in this matrix. Analogously, the probability for S1 equal to 1 is 0.4648. So this pixel is almost equal likely to be black or white. And so from this, we can calculate the entropy of S1. As expected, it's almost 1 bit. And one can assume ergodicity, which means that different pixels have almost the same marginal statistics and thus the same entropy. We denote this entropy of a pixel simply as HS. So the coding capacity used to represent S1 and S2 separately in their raw input form is then about 2 bits. We can then also calculate the joint entropy from the joint probability distribution, and this gives us 1.1434 bits. This is the actual amount of information represented in the two pixels, even though we used almost 2 bits to code the information. So therefore, the raw input representation is inefficient or redundant, and this is the redundancy. It's 74%. This is because given the information of 1 bit, almost 1 bit in S1, the additional information in S2, once S1 is already known, is only 0.1470 0 bits. And this is the conditional entropy of S2 given S1. And it's small because the conditional probability of S2 given S1 is very peaked for S2 equal to S1, as you can see in this 2x2 conditional probability matrix. In this matrix, the diagonal elements are very nearly equal to 1. So that means S2 takes the same value as S1 in, for instance, in 98% of time, both when S1 equal to 0 or S1 equal to 1. And this peaked probability distribution can be visualized in this plot. We can do the same calculations for this grayscale image. And so this gives the joint entropy as 11.3 bits. However, each pixel has an entropy of 7.63 bits. So the two pixels together requires 15.3 bits to represent the information. So the redundancy of this representation is 35% to represent the 11.3 bits of information. So as we change from a black and white image to a grayscale image, the coding resource is increased from about 1 bit per pixel to almost 8 bit per pixel by a factor of 8. The total information in the two pixels increased from 1.14 bits to 11.3 bits by a factor of about 10. This seems to be a good return, so the redundancy decreased from 74% to 35%. In the book, you can look up a reference to explain that this decreased redundancy is partly due to noise or pixel information that contains no image object information. Noises are not correlated or redundant between pixels, and that's why. So therefore, perhaps 8 bits of resource to represent each gray level pixel detail may be an overkill. 6 bits may be sufficient. So for example, if in an n pixel image, the raw representation requires 100 bits of coding resource, but the total actual information is only 50 bits, it would be nice if we could transform the pixel representation to another more efficient representation before we transmit the information down some information channel. This joint entropy, 50 bits in this example, is the Shannon limit, a lower bound for any encoding transform. In practice, it's difficult to reach this limit. Information redundancy is, however, useful for error correction. For example, if you have this English sentence with this string of letters, each missing letter due to error is denoted by a dot. It may be any of the 26 letters or a space, so altogether it can be any of the 27 possibilities with a prior probability distribution of PS. So each letter requires this many bits of information to narrow it down what it is. With 27 possibilities, this entropy would be up to almost 5 bits. Since 2 to the 5 is 32, that's more than 27, so 5 bits is sufficient. However, we can guess the missing letter by context because the conditional entropy given contextual letters is much smaller than 5 bits. And if this conditional entropy is nearly 0, then this means we have no uncertainty about the missing letters given the context. So in this example, we can guess the original sentence from context. So redundancy in language enables us to understand, for example, foreign accent or vague articulations. So how much redundancy is optimal? That depends on how many errors that need to be corrected. So if you still cannot understand the sentence, you can always ask the speaker to repeat the sentence. This repetition increases the redundancy as you make somebody redundantly speak again.